Friday morning. Start with a little music this morning. We'll give people a couple minutes to get on here, and then we'll get started. Looks like nobody here yet. Oh, somebody's here. Good morning, Daisy. Morning, Maria. Okay, I think we can get started. So, as we talked about yesterday, last night, I guess it really wasn't that long ago, huh? Well, welcome everybody. We're going to look at the rest of the notes for today and kind of bring together everything we did last night with some new information about electrons. All right, so make sure my pen's going here. Yep, looks good. Okay. Okay, I fixed my mouse thing too, so that's good. All right, so we said at the end last time that ultimately we want to be able to solve these types of problems where we can say, given a particular symbol, can we sort of decode that symbol and figure out what it means in terms of different types of subatomic particles. So before we do that, let's go back up to where we left off before. So we can talk a little bit more about ions. So we talked about protons and neutrons. And we said that protons give us the type of element that it is, so that the actual type of atom is determined by the number of protons, which we call the atomic number. And the atomic mass, or the mass number, is given by the protons and the neutrons together. But there's this other part called the electrons. And the electrons are around the outside, and we talked yesterday about how they can be removed. They can be taken off. They can also be added to. So what happens is either atoms can lose electrons or they can gain electrons. And in doing that, their overall charge changes. So, for example, where'd my thing go? There we go. So for example, if we look at sodium and we just write Na, we're talking about the sodium atom, the neutral atom. And if we look that up on the periodic table, pull that up again. Okay, so sodium, you can see over at number 11 on the far left there. That's in the alkali metals. Sodium has 11 protons. So just by seeing this symbol like this, we know that this particular species or this particular atom has 11 protons. And we also know that it has 11 electrons because there's no charge here. And if there's no charge here, we can assume that number is 0. That's really what no charge means. And so the positive protons and the negative electrons balance each other out, and we have a neutral atom. Okay. So if that sodium were to lose an electron and instead become something with, change colors here again, and instead become Na with 11 protons and 10 electrons, so it's lost an electron. Now we have one fewer electron, and so we're going to call that Na plus, or sodium plus, sodium ion. Notice that, and this is sometimes a problem, notice that we have a positive charge here, but we haven't changed the number of protons. So sometimes people want to add protons to increase the positive charge. So, oh, it's +1, that must mean it has an extra proton. Well, it does mean that it has one more proton than electron, but we can't add a proton because that would change the atom. If we added a proton to sodium, we'd actually have magnesium now, not sodium anymore. So the protons have to stay the same. The electrons can change, and that's what makes different charges. Oh, good morning, Monica. Also, I didn't say good morning before. I didn't see that note. Anybody else around? If you want to say hi, I'll try to keep an eye on the chat here and say hello. Okay. So that said, there are several elements throughout the periodic table whose charges are predictable, sodium being one of them. And by predictable, I mean when they're neutral, and when they're charged, they always carry the same charge. And this is actually a figure from our book. You can see like all the alkali metals carry a +1 charge as an ion. So that means that for an alkali metal, it's really only going to be two possibilities. You're going to have the neutral atom with equal numbers of protons and electrons, or you're going to have the ion with a +1 charge, meaning one fewer electron than the protons. Similarly, the alkaline earth metals just next door are always going to make +2 ions. And then on the other side of the periodic table, we have our noble gases way over here, which I'm covering up, but that's fine because they don't actually make ions readily, so we don't even worry about those as having ionic charges. And then the column right next door, the halogens, those, when they're charged, tend to make, I'll try to get out of the way there. When they're charged, they tend to make a -1 charge. The ones right next door here, -2, -3, and then, yeah, it's possible -4 here, but really, I'm going to highlight a couple here that you should know, because all of these, you can see they kind of get tricky, but you should definitely know these. Try that again. You should definitely know those. Those are always going to be +1 and +2, and that's going to be really helpful for figuring out some other stuff. You should also know that these are going to be -1, and actually I'm going to abbreviate that a little bit. That bottom one, acetine, is not a common, it's radioactive and it's not commonly used, so we don't really have to worry about that. And then these are -2. So those are all very predictable. -1, -2, -3, and then +1, +2. So the ones in the middle, even though they have some like some of them only have one charge, like zinc only makes a +2 charge, cobalt doesn't only make a +2 charge. That's not quite right. And manganese certainly doesn't only make a +2 charge either. I'm not sure where I think these are just some of the most common ones. I'm not crossing these out because they're wrong. I'm crossing these out because we don't need to worry about them for our class right now for the charges. Aluminum is so common that that's a good one to know also. So if you know +1, you can see the pattern here, +1, +2, and then +3. And then going from the other side, you've got 0, -1, -2, and -3. All right, so I don't think that's too much to worry about. And when we start putting these things together to make ionic compounds in, I think the next chapter or maybe a couple chapters, you'll see that, and with practice, you'll start remembering those even more. Okay, so now knowing that stuff, and one other thing we should note here, when I wrote down the symbol sodium and I said, okay, if we have a neutral sodium, that means it's 11 protons and 11 electrons. I didn't specify a number of neutrons, and that's because we can't know the number of neutrons directly from the symbol. There's no way to know that. We can't know that mass number. We have to either be given the number of neutrons or the mass number itself so that we can figure that out. There's no way to just kind of look that up. And if you recall from last night, that's because there are different isotopes. So there are actually different numbers of neutrons that it could have, all with the same symbol. So we need to know which isotope we're talking about. Okay, so in general, we can think of a chemical symbol as kind of looking like this. And we've talked about what these different spots could be. So A is generally the mass number if it's there. B is going to be the atomic number, again, if it's there. If that's not there, then we just reference the periodic table, because as long as we know the X, the symbol, we can look up the atomic number and therefore know the number of protons. And then C up here is what we just talked about. That's going to be our net charge. So the overall charge, the difference between the protons and the neutrons. All right, so that brings us to this table. Yes, question, go ahead. Okay, good question. I think I know the rest of your question, but go ahead and keep typing. On the worksheet, uranium's mass is 235, but on the periodic table, it's 238.029. So what's going on there? Yeah, that's an important distinction. So let's pull up our periodic table again. So if you look at the periodic table, there are these numbers underneath each element that are kind of like mass numbers. Those are not exactly mass numbers. Those are averages of all the mass numbers of the different isotopes and their abundance on Earth. We use those numbers for some mass calculations that we'll get into a little bit later in the class, but that's not the mass number. That's not actually the same number. And one way you can tell that is because of the decimal nature of it. So the fact that it's not close to an even number, some of them are, but it's not close to an even number, tells you that that something else is going on. It's some sort of an average. So, so yeah, like on the worksheet over here, pull that up. Our uranium down at the bottom is 235. That's because we're now talking about this specific isotope of uranium. We're saying we care about uranium-235 at this moment, and that's what we're going to base our stuff on. There are other isotopes of uranium as well. So the question is, if you round it up to 236 or 239, is it correct? It's not, because those are different isotopes. There's uranium-235, there's uranium-238, there's uranium-236, there's probably other ones too. So we need to know which one we're talking about. There is no official mass number on the periodic table because there are multiple different possible isotopes. So that's actually a good way to look at this table here. So let's look at this one, uranium-235. If this just said U, if it just had a U and there was no number there, we could not find that number because we don't know which isotope we're talking about. It's not on the periodic table. It's not about rounding it from the periodic table. It's just, we don't know. We don't know which isotope we're talking about. So in order to find all the numbers of subatomic particles, we need to know which isotope are we talking about. And in this case, it's specified as 235. So we're talking specifically about uranium-235, which is the uranium with 92 protons and 100 and, what would that be? 140, 100 and, what did I say? I'm getting confused now. 92 protons. So our mass number is 235. Put this up for you. And so then, yeah, so how many protons is that going to be? It's going to be the difference between these two numbers, between the overall mass number and the number of protons. All right, so 235 minus 92 is 143, right? It's a little early in the morning for math in my head, but I think that's right. Yeah. All right, thanks, Maria. Yeah. So what we got 143. All right. So this specific example is uranium-235, 143, which has a mass number of 143. Let me get an extra page in here so I can move that up. All right. So let's head back up to the top of this and look at the example here, which is sulfur 2 minus. Let's see, why can't I move this one? Yeah, it's the same for all the elements. So actually, yeah, let's look down at this one because this is a little bit different looking. If we look at this zinc, it says zinc 2 plus. All right, so we're given some information here. We're given that it's zinc, and we're given that the charge is +2. But notice we're not given the mass number here. So which isotope are we talking about? Do we look this up on the periodic table? Well, again, we can't find the mass number from the periodic table. So in this case, the only way that we can do that, or the only reason we can do that, is because it's given right here. So here's our mass number 38. It just wasn't in the symbol. So really that should be the complete symbol. So we should complete that way. And then we can figure out the rest of it. So notice this other column right here, average atomic mass. This is the number that's going to come from the periodic table. But the mass number, that number that goes up in the upper left, does not. And yes, that is a cation. So let's write down those terms also. We can do that here. I don't remember if it was up there or not. But there are two ways to name ions. There are cations, which is an ion with a positive charge. And there are anions. All right, so cations and anions. So yes, this one would be a cation. All right, so before I go through the rest of this, well, let's finish up this uranium one that we started. So we got 92 for the atomic number and 235 for the mass number, which we get from the symbol, not from the periodic table. Then from the periodic table, we can get the average atomic mass, which is 238.029. Sometimes, by the way, that number can give us a clue as to which is the most abundant isotope on Earth, but sometimes not. So for uranium, it is actually true that uranium-238 is the most common isotope on Earth. It's a very stable isotope. That's what sometimes that's known as, I think that's what's called depleted uranium. Uranium-235 is much rarer. That's the nuclear, that's like what can power a nuclear reactor. And so part of when you hear about like countries trying to get nuclear capabilities, really those capabilities are the ability to separate the isotopes of uranium. So you can isolate and concentrate those really fissionable isotopes, the ones that can be broken up in a reactor like 235. Takes some very specialized equipment to do that because those masses are so similar. All right, so the columns we still have are the net charge, and whether it's a cation or anion. In this case, it's 0. There is no charge there. And then the final column is the number of electrons. Since the charge is 0, that's how we know the overall. I'll this up out of my head here. Since the charge is 0, that tells us that the protons, which are positively charged, have to equal the neutrons, which are the electrons, sorry, which are negatively charged. So protons and electrons have to balance out because the net charge is 0. So whatever the net charge is, that's how you figure out how many electrons there are. All right. I want to go through this so to make sure that you can do it, but I want you to try it first because I think it's important that you do that. And yes, that is a neutral atom. That is correct. So that's a neutral atom, not an anion. So we might call that a neutral atom. All right, so if you have this, if you have a way to annotate on your screen, or if you just want to copy it on a piece of paper, I want to take some time and see if you can finish this up by yourself. Use a periodic table for reference, but otherwise, see if you can do it. Take about 5 minutes or so. If you get partway through, whatever, I want you to see what you're getting right and wrong instead of just copying what I'm copying. So making sure that you can do it yourself. So let's take about 5 minutes or so and do that. I will put the periodic table back behind me so that you can see that. You can pull this down, these notes down to get the rest of it, but let me know if you're missing something or if you want to see something. I might be covering up some of the things, but I'm sure you can find a periodic table. Can kind of move up here a little bit. All right, so let me know if you've got questions, but see what you can do with that table. If you're done, you can also let me know in the chat and we'll move on. I don't really have a sense of how long this is taking you. Also, if you're just totally stuck and you're not even trying it. Okay, yeah, we'll go through it. I just want to give everybody a chance to try it. Okay, great. Well, let's go on and go through them. Now, as I'm going through, if your numbers are different and you don't understand why, let me know. Put a message in there or something so that we can check and see what's going on. All right. Move my periodic table here. So we've got 40K. So potassium is number, I think it's 19. Is that right? Yeah. 19. Mass number is 40. We get that from the symbol. The average atomic mass is on the periodic table, which I can't read that, but it's the number that's here. It's too small for me. So whatever you got, that's what that is. 39 point something, I think. The net charge here is 0, and that's an atom. Was it 39.09? Thank you. All right, so now these we get from the symbol and this information here. So the protons are 19. Neutrons are the difference because the mass number is the neutrons and the protons together. So that's 21. And then the electrons in this case are going to be the same as the protons because the overall charge is 0. All right, so far so good, hopefully. Let's move on to the next line. This time, we don't have a chemical symbol to start with, but we do have protons, neutrons, and electrons. So with that information, we should be able to get everything else. So we can kind of start wherever you want. Probably the easiest is protons, atomic number. Those are always, always, always the same. So that's easy. Those two columns should always be the same. Our mass number is the protons and the neutrons. So 15 plus 17, which is 32. And then we'll get the mass from the periodic table once we figure out what this is, but let's look at the net charge. The charge we can get from the protons and the electrons. We've got 15 protons and 18 electrons. So that means we have more electrons than protons. Since electrons are negative and protons are positive, that means we have 3 extra negatives. So our net charge here is going to be minus 3, and that makes this an anion. All right. Now, the other thing to note, you've probably seen this, sometimes you see the charge written 2 minus and sometimes minus 2. Those are interchangeable. You can use that. You can use either way. The reason that the number comes first here sometimes is because if you have multiple symbols together, it can get confusing if you have minus 2 and then some other symbol, because then you don't know if the 2 goes with the first one or the second one or whatever. So it often makes it a little clearer to do it this way, but it's not wrong to write it this way either. Okay, so now we got everything we got from the numbers here. So we need the periodic table for the rest of these. We look up element number 15, which is phosphorus. And so that's going to be a P. Oops, let me change that again. And then 32 here. We also need a charge because this is 3 minus, so we need to make sure that's there. And then if we want, we can also write the atomic number underneath, 15 down here, but that's not necessary. Average atomic mass, again, we'll get from the periodic table, which again, I can't see. All right, moving on to zinc. So this time we're given the symbol and the mass number and the charge, but not the numbers of particles. So we can look that one up on the periodic table to get the atomic number, and that is 30. Which also means there must be 30 protons. The mass number 38 means just 8 neutrons. That probably doesn't exist, most atoms have a relatively balanced number of protons or neutrons, or they have more neutrons than protons. So this was probably just made up for the sake of this worksheet. And then the number of electrons, we've got 2 fewer electrons because our overall charge is +2, and that's given by the symbol right here. Average atomic mass, again, that's going to be the number on the periodic table. Any questions so far? How is it going? Are you getting them? Did you get them, most of these blanks, correct? Great, good job. Don't worry if you didn't get them correct. Just think about if there's a particular column that you keep getting wrong, go back and think about where those numbers come from and how you can figure those out. So we got a couple columns to go. This next one, we're looking at element number 35. So that's the one with 35 protons and 46 neutrons. The charge here we can get from the protons and the electrons. Whoops, move this up here so you can see it. So this is 35 protons, 36 electrons. That's a -1 charge. So now we have all the information here. We look this one up and we can see that it's bromine, Br. The mass number is 81 and the charge is -1. Generally, if it's -1 or +1, we don't put the 1. We just put a minus or a plus. So bromine's an interesting example. I think if we, I know this one is 79.90. If you look at that on the periodic table, you think, oh, that's pretty close to 80. I bet 80 is the most common isotope of bromine. But actually, bromine 80 doesn't exist. There's bromine 79 and there's bromine 81. And they're about half and half in nature. And so the average between those then is about 80. And that's where that average number here comes from. So bromine 80 as an isotope actually does not exist. Will this be on the, will what be on the exam? Like all this stuff, like finding all these numbers and stuff? Yes. Yes, it will be on the exam. All right, our last column then, we have fluorine 20. So our mass number here is 20. We can find the atomic number from the periodic table, which is 9. The charge here, it's kind of small, just the way the font works, but this one was -1, so that's an anion. And that means we have 9 protons, 11 neutrons, and 10 electrons. We need, remember, 1 more electron so that we get the -1 charge. All right. How do you feel about that? Generally okay? Yeah, you'll always have a periodic table. If we were, I mean, think about if we were like on campus, there'd be a giant one on the wall all the time. So what did you get incorrect about it, if you don't mind sharing? Oh. Yeah, I mean, I think it's really small, right? Yeah. So that's, I wouldn't worry too much about that. Hopefully on something like an exam it would be more obvious when with that. So you rounded. What did you round? What do you mean? You rounded the 9 to 10? The mass. Oh, so you looked it up on a periodic table and then put that here? Yeah. So this number is, remember this number here, it comes from the periodic table, but this does not. So the only way you can get that is either from the symbol itself or from the protons and the neutrons added together. Not from the periodic table. You cannot get that from the periodic table. Okay, great. Okay, the very last thing, it's not actually in these notes because we're going to get into it a little bit more in a future packet, but it is on the homework, so I wanted to just discuss it quickly, and that's this. It is a little bit earlier on this packet, but this is this concept of valence electrons. The valence electrons, I think it's spelled incorrectly in the packet too, so watch that. This is the correct way to spell it. Valence refers to the outermost electrons in an atom. And so every atom has what we call the valence electrons, which are on the outside, and the core electrons, which are on the inside. The reason that this is an important distinction is it's the valence electrons that actually do the chemistry. That's what's making it do the things that we're going to talk about for the rest of the semester. So it's important that we know how many valence electrons a given atom has, so that we can, well, you'll see some of the consequences of that. So every atom has the valence electrons and the core electrons. To find the valence electrons, what we do is we recognize that there are different areas within the atom that the electrons can be. And this is sometimes called the Bohr model. If you look in the textbook, there are some more detailed explanations about it. But the way I like to think about it is with buckets. And I think people have found this to be useful. So we're going to draw 3 buckets, and the reason that I draw them here is like this is because this is kind of on an energy axis. So this is energy, meaning that as we go up in bucket, we also go up in energy. And this bottom axis is going to be the distance from the nucleus. So this is the nucleus, like way down here. And then as we go up in bucket, up in shell, whatever you want to call that, we get farther away from the nucleus. Bucket 1 only holds 2 electrons. And then buckets 2 and 3 hold a maximum of 8 electrons. And E with a little minus sign is our symbol for electron. So how this works is you take a particular atom and you figure out its number of electrons, and then you use it to fill these buckets. So, for example, let's take sodium. And we want to know how are sodium's electrons distributed in these buckets, in these levels? How far from the nucleus are they? So what we do is we draw our buckets, and eventually you won't need to draw the buckets, but it's helpful to just see it. So we've got our little 2 bucket, and then our 2 big buckets. And we figure out how many electrons a neutral sodium atom has. So to do that, we would look at the periodic table. We'd find the atomic number, which is 11. And that means that a neutral atom has to have 11 electrons. And then we place those electrons in the buckets, starting from the bottom and going up. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the reason I distributed them in that way is because the bucket is full. We're saying it's full at 2 for number 1, at 8 for number 2, and then at 8 again for number 3. So we can put the first 2 in number 1, and then we have to jump up to number 2. We can get 8 in there, and then we have to jump up to number 3, and there's 1 left in there. So the outermost electrons, the ones in the highest bucket, or the furthest out bucket, those are the valence electrons. I see your question, just a second. So these are the valence electrons, and then these all together, all the rest of them, are the core electrons. Now, if we only had, let's say, 3 electrons, then number 1 would be the core, and number 2 would be the valence. So we would say that a sodium atom has 1 valence electron and 10 core electrons. All right, so the question is, if it has more than 18, do we add another bucket? Well, yes and no. Unfortunately, what happens is if it has more than 18, it gets complicated. And yes, you add more buckets, but it's not quite as straightforward as this. If you want to look, I believe the book talks about how to do that. If you want to know, in our class, we're not going to focus on the complicated ones. If you go on and take general chemistry or something like that, you'll learn all those nuances of how to arrange the electrons. For us, the important thing is how many valence electrons and how many core electrons. And really, how many valence electrons is really the important thing. So because one thing you might find then, as you go through this, if we look at the periodic table, look at how these rows are arranged up here. So we've got the very top row has 2, the second row has 8, and the third row has 8. So the periodic table is arranged based on these same sorts of electron groupings, and that's because how many valence electrons an atom has controls or contributes to its chemical properties. So atoms with the same number of valence electrons are going to have similar properties, and that's how we group those into the families, like alkali metals, alkaline earth metals, and so on. So you can see sodium all the way over on the left has 1 valence electron. If you do the same bucket thing for lithium with 3, it also has 1 valence electron. It's just that that 1 is in bucket 2 instead of bucket 3. And if you could do the counting going on and on with more buckets, you'd actually find that everything in that first column has 1 valence electron. So eventually you'll find some ways to see some regular patterns in the valence electrons, and we'll get into that in a future in some future topics. But I do want you to see that. So how about the nonmetals? Yeah, so the nonmetals can work the same way. So let's try a nonmetal. Get rid of my image here. Let's do oxygen. Oxygen is element number 8, so that means it has 8 total electrons. So we can fill our buckets with 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. All right. So now in this case, there's nothing in this shell at all. So that one kind of doesn't matter for oxygen at this point. So we make our separation here, and we call this the valence, the number 2 the valence, and number 1 the core. So oxygen has 6 valence electrons and 2 core electrons. Did you see how that works? And actually, if on the periodic table, that works as well. So everything in oxygen's column over here, oxygen, sulfur, selenium, tellurium, also has 6 valence electrons. And if you're really paying attention or really focusing on some details, you'll also see up here, look at the column number. There's various ways of numbering the columns that have been developed over the years. Sometimes it's column 16, but more commonly it's called column 6A. And that's helpful because actually all the elements in column 6A have 6 valence electrons. Notice over the sodium's column is 1A, and sodium has 1 valence electron. 2A has 2 valence electrons. The ones in the middle, the transition metals, unfortunately that doesn't work. But the two extremes, the two sides, the 1A and 2A, and then 3A through 8A, the number of valence electrons is that column number. So that can be helpful, and this is where you get that from counting up these buckets. Unfortunately, the bucket thing only works, as we said, for the first 3 rows, and then it starts to get a little tricky. But the column number part works throughout the whole periodic table. So if I said, how many valence electrons does, let's say, what can we see here, like selenium have? We can say, selenium's in column 6A, so it probably has 6 valence electrons. And even if we didn't know how to count all that up with the buckets, because again, it gets complicated, we can still say, we can still be pretty sure that selenium has 6 valence electrons because it's in column 6A. All right, so that should give you everything you need to know to complete the homework this week, to complete the packet. And any other questions or other things you want to go over before the weekend? I will be around this weekend, by the way, so you can send me questions and stuff like that if you've got them. Nothing? Everybody good? All right. Well, thank you for joining me this morning. I hope everything's going well with you, and I will see you next week. Bye, everybody.